if you were here for Shane Lynn's talk, there's probably going to be quite a bit of overlap because they're pretty closely related areas. So I'm going to start with just kind of a general background, what we do, what type of work we can do in legal text analytics. Then I'll talk a bit about some traditional legal text analytics pipelines, so what the workflow looked like up until about a year and a half ago when things started to change pretty dramatically. Then I'll talk about neural networks in general, convolution networks in particular, and then the application of convolution networks to text data. So first things first is, I suppose, the background, bright flag, what we do, the types of classification tasks we might be interested in. So we're a legal invoicing analytics company. So basically we take legal invoices from people who outsource their legal services to third-party companies. So companies who spend millions of dollars and millions of euros every year with legal providers. They get back an awful lot of information from the lawyers, but what their lawyers are doing at a pretty low level of granularity. So when a lawyer wakes up in the morning, he starts a clock and he starts counting money. So basically every 15-20 minutes when a lawyer completes a task, he fills out a time entry for that task in a time entry system, and that task is billable to some client or another client. So in this example, we have two kind of sample detailed lines from invoices by a lawyer, Rachel Smith, on the 1st of October 2017. She spent half an hour discussing terms of a pro hac vice motion with John Smith. And later on that morning or later on that day, she spent an hour and a half discussing conducting a Johnsville bill of sale review. So what types of classification tasks might we be interested in here? What types of classification models might we want to build? So I suppose the first thing that we might be interested in is the general type of action that's being carried out. So is it a discussion? Is it a phone call? Is it a meeting? Is it someone drafting a document? Is it someone attending court? Those sort of general, not necessarily legal specific actions that lawyers might carry out over the course of a day. The second thing we might be interested in is the direction of that action. So in the first line, we're talking about a discussion with a person named John Smith. So the context there is very important to try to figure out what's actually happening in the line, who is John Smith and what's John Smith's relation to the firm who's working for the particular client. Because if you're outsourcing your legal work to a law firm, you might be perfectly happy for them to bill you for meetings with you or for meetings with opposing counsel, but you don't want to bill. You don't want to be billed for discussions with their own internal team, because that's stuff that they should be carrying by themselves. And similarly, in the second example, we have a Johnsville bill of sale review. So the context of the review might be in relation to a particular matter relating to a company or a town called Johnsville. And the kind of third type of classification that we're kind of interested in is a bit more specifically legal, and in some ways a bit more straightforward, because legal language is kind of, it's quite technical and tends to be quite specific. So we're discussing terms of a pro hac vice motion, and we're reviewing a bill of sale. So we want to create classification models which allow us to identify within legal invoices particular legal content types. So we're not just interested in the general action type, we're interested in the specific legal contexts, because when you're looking back over all of your invoices at the end of the year, at the end of the quarter, you want to see how much time has been spent, say, on a particular motion, or how much time firm X spends on a particular motion versus firm Y spends on a particular motion, to see who's actually doing the best job for you. So that's kind of the business background. In terms of, I suppose, how solving these text classification problems might have looked at up until very recently, and this is kind of overlapping a bit with what Shane was talking about. Kind of a typical sort of text classification pipeline might have seen us taking an invoice into the system, tokenizing that invoice, so breaking up all the words into individual words, maybe cleaning out punctuation, transforming them into a lowercase form, lemmatizing the words. So we want to make sure that we we only get the canonical form of the word if at all possible. So we want to treat, say, regards and regarding and as the same kind of canonical form of the word. Dictionary creation, so we want some sort of dictionary or index that allows us to go from a word through lemmas into kind of a dictionary form that we can use to create a matrix for our models. N-gram extraction, so we typically spend a lot of time figuring out what are the n-grams or the multi-word groups in our text. The word say motion to dismiss and motion to compel in legal circles have very different meanings to the word motion on its own. So the individual word motion means one thing, but in the legal context there are all these various different subtypes of motions, and I suppose before some of the advances we've had in the past kind of year and a half, 2 years or so, we would have spent a bit of time building n-gram extraction models to figure out what the relevant n-grams in the data set were. Part of speech tagging again, I mean a lot of these a lot of these steps are still steps that we carry out, but the focus of the work, at least I find anyway, the focus of the work has kind of shifted away from spending a lot of time in these sort of data preparation type steps. So part of speech tagging, where we'd train a part of speech tagging model to recognize what part of speech particular words in the sentence represent. So is this a noun? Is this a verb? Is this a conjunction? So on and so forth. Dependency extraction, again, for any given word, what's the root of that word? So what's the word that the word is dependent upon for its meaning? Feature selection, you're probably getting the sense now that at the end of this big massive pipeline of work, we have an awful lot of features to input into our model, so we typically spend a bit of time trying to figure out what the best subset of features are, what the best set of parameters for all of those pre-processing steps are prior to inputting the model, and then some sort of normalization. So typically, if it was a bag of words model, you do something like TF-IDF normalization. So look at the frequency of term in the document you're looking at versus the frequency of the term in the corpus as a whole. So in your whole data set, the idea or the intuition being behind it, you want to weight terms more highly which occur less frequently in the overall corpus. The output of that typically is going to be a document term matrix or a document matrix, and you feed that then into a machine learning model. Usually for these sort of text classification types, SVMs work really well because they work very well with sort of very, very sparse data. So that's how things used to be, and to some extent it's how things still are. But in the last kind of year and a half, 2 years, since kind of word embeddings, recurrent neural networks that Shane was talking about, and convolution neural networks that sort of come on stream, a lot of this workflow has changed pretty dramatically. So I'm going to move on to neural networks, and I'll start just by giving just a brief kind of overview of neural networks in general. So on the slide, you can see a representation of an artificial neural network, and I suppose there's a lot of kind of media hype at the moment about neural networks, and I always think if they were named slightly differently, there might not be quite as much hype as there is. But basically, this is a classifier. It takes an input, it carries out some transformations, and then it delivers an output at the other end. The data input and the data transformation steps in the network are arranged in layers of nodes or neurons. So typically you have an input layer, an output layer, and one or more hidden layers which carry out the transformations to the input to create the output prediction. This kind of makes more sense when you kind of look at it at the level of an individual neuron. So you'll notice that there are kind of multiple vertices connecting each of the nodes. So every single node in each layer is connected to all of the nodes in the previous layer. And those connections are all weighted. So what we're doing with the network is we're trying to learn the weights which map the input shape to the output shape with the highest level of accuracy. So if we actually kind of zoom in and take a look at an individual neuron, so we're looking here at one of the neurons in the hidden layer. So like I said, we can see it's connected to each of the neurons in the previous layer, and there's quite a simple transformation happening at the level of the neuron. So we have a weighted sum over each of the inputs, we add a bias, and then we apply an activation function, so a sigmoid function in this case, so that we can actually create a nonlinear model. If we didn't apply this function, or if we didn't apply this function across the neurons, then we basically just have a linear model that was just adding up weighted sums. And there are, and obviously a number of different activation functions which we can use in these models. Typically at the moment, rectified linear units seem to be kind of giving the best results. And in most of the literature and the community, that seems to be what most people are using, but these things change as well over time. So I suppose the next question is, how does it work? So I won't go into a huge amount of detail here. Basically when we're training our neural network, we can think of it as operating sort of in two modes. We have a forward pass, and then we have back propagation of the signal back through the network. So in the forward pass, we calculate the activations at each of the nodes in the network, feeding the data forward through the network to give us our final prediction. And I suppose one of the kind of key things here is that the activation at any given point in the network can be expressed as a weighted sum of the activation of the previous points in the network. And back propagation then is kind of when we take those weights and we train them or optimize them to reduce some sort of cost or a loss function. The loss function is arbitrary, really, so as long as it can be expressed in terms of your outputs, and as long as it can be expressed in terms of an average, you can use pretty much everything as a cost function. Sorry, anything as a cost function. So once we've kind of calculated the overall cost function, what backpropagation does is it calculates the gradient at each point in the network in relation to that cost. So it calculates how much the cost function would change for a change of the weights at that node. The idea being that if the cost function would decrease massively for the change of weights of a particular weight in the network, then you increase that weight. If the cost function would increase massively or would increase for a change of weight at a particular node, then you go in the opposite direction. So that's a very quick kind of summary of neural networks. The next question is, so that's kind of neural networks. That's kind of the classic topology. What do we mean when we talk about convolution neural networks? And to talk about convolutions, we don't have to start with images, but I suppose the big jump kind of came in image recognition tasks. So if you see an image on the left-hand side of the screen, you can see it's an image of a storm, and to us we can see waves crashing up against the coasts, houses writing on the walls, and so on and so forth. To the model, that machine is actually 3 channels with 2 dimensions each. So we have a red channel, a green channel, and a blue channel. And that's kind of key to kind of, I suppose, figuring out the main intuition behind convolutional neural networks. Because one thing you're probably asking yourself now is, like, how would you apply a normal densely connected network to an image recognition task? Because on the face of it, it presents a couple of different problems. One problem is that your image would effectively have to be centered around the same points for every example that you train the network on, because the network if all of the nodes are densely connected, then all the nodes presume that the information at point 220 in the image or point 320 in the image should always be at point 320 in the image. So it expects to kind of see the same thing in the same place every time that you're actually you're training or scoring your network. Another kind of thing to think about is that there's an awful lot of information in images. So if we have 3 channels for red, green, and blue, and you have each of those channels, densely connected to a hidden layer, you have an awful lot of weights that need to be adjusted to train your model. So it's not necessarily a very efficient way of training a network. So this is sort of where convolution nets come in. And basically what they do is instead of connecting each node in the hidden layer to each node in the previous layer, it creates a number of filters which are connected to or mapped to particular points in the input layer, and the filters sort of slide. The metaphor goes, the filters sort of slide over the input image, and instead of learning weights, the network is actually learning filters for the image. So it probably makes a bit more sense if you look at an example. So on the left we have a kernel function, just a 3x3 matrix, and the green box on the right is an image with the kind of the yellow box being the point in the image that we're actually calculating the kernel for at a particular point in time. So you can see the convolved feature is calculated basically by getting the dot product of the kernel on the left and the image on the right. And what the network is doing is it's learning the best convolution or the best kernel to transform an image into something that makes sense in terms of a classification output. I kind of find it makes sense sometimes, and typically when you build these networks, you build them out across a number of different layers, and it makes sense. I kind of think of the convolutions as sort of learning sort of higher level features about the image or higher level features about the text. So you expect the convolution should recognize things like kind of lines and edges and changes of shape in maybe the first layer, and then you typically have a pooling or an aggregation layer, and then the second layer then recognizes slightly more general features, and the third layer then recognizes kind of more general features again before you feed it into a number of densely connected layers. So you can kind of see in the example on the screen kind of stacked convolutions in the kind of grey boxes on the right hand side, where the box on the left is sort of recognizing or activating for particular sort of basic shape types. The box on the right is activating for facial features, and then the box on the far right is activating for kind of more distinct facial types. So that's I suppose the intuition behind using convolutions. It's how they're used for image classification. Next question is how do we apply that to text? Because text and images look pretty different, right? So we think about a text, let's say call with Murphy and Co. Read preliminary injunction, and we can think of it from one point of view maybe as a list of indexes, where each index corresponds to a word in our dictionary. We can maybe take that or maybe abstract that a little bit and create something like a dummy code. So now you have a two-dimensional vector for each sentence, where the dummy codes basically represent your original index. With dummy coding, it's not very efficient, in part because you get really high dimensional input data into your models, and it doesn't really take any account of kind of distributional features of the word. So the previous talk, we kind of Shane was talking a little bit about word embeddings, and we typically actually use them a lot for these kind of applications, because apart from being more efficient in terms of the dimension of what you're feeding into your network, they also capture kind of distributional features of the words. So I have an example embedding that I loaded. So this is an embedding trained using GenSim on kind of legal invoice data. So I'm going to get the most similar words to call in my data set. And you can see it's kind of picked up on words that pretty much mean the same thing as call. So we have calls, teleconference, meeting, TC, teleconferences, meeting, conf, discussion, teleconf, coordination. So you can see it's actually done a pretty good job of kind of recognizing the the space in that higher dimensional, the area that kind of corresponds to this sort of concept of call. And you can see if you actually just look at it, it's basically representing it as a 100 dimensional vector. So we typically tend to use word vectors rather than dummy coding for input into our convolutional nets. But in terms of I suppose how the convolutional nets look in practice in text, it's not dissimilar to how convolutional nets process images, in that you're effectively passing a kernel function over your text. So if we have an input text here, which is call with client, read counterclaim, and we're representing that in a 5-dimensional embedding on the right hand side, we can pass a kernel function over the input text and create an input map, a feature map of that text. And typically then we'd pair that with a max pooling step to get the most relevant feature for the classification task that we're carrying out. I suppose the next stage then is building nets which kind of use multiple of these convolutions. So you typically use combinations of convolutions of different filter sizes. So I usually find the kind of filters of size 2, 3, or 4 work pretty well. I think intuitively it makes sense, even if you take a step back to how we kind of used to do things before, and we used to extract n-grams from the text. I still think that the core unit of the text is still 2 or 3 word phrases. You can layer it with further convolutions to pick up on kind of higher levels of meanings, and that's a way of allowing the convolution to see all of your text. But usually kind of 2, 3, 4 with convolutions seem to work pretty well in practice. So here we have two filters of with a 2 and one filter with a 3. We have max pooling over those filters, and then they're concatenated into an output vector representation of our text. Some other kind of parameters that you kind of typically play around with for kind of training convolutional nets. So in the previous example, you would have seen that the filter kind of moved one step at a side through the input, so it was moving with a stride size of 1, but you can set the stride size to any arbitrary value. In practice, usually a stride size of 1, a stride size of 2 tends to work best. And padding as well is kind of something, again, you can do if you want to do it, but I suppose if you think about a convolution passing over the text, it's going to get all the convolution. It's going to learn its filter based on all the combinations in the center of the word, but it's not necessarily going to learn filters of kind of words at the start or words at the end of the string. So by introducing padding, you just allow it to create convolutions based on the fact that a particular word or particular 2 or 3 words are at the start of a sentence rather than at the end of a sentence, or rather than the middle of the sentence. Okay. So I'll just visualize a few examples. So I was think it's kind of strange when people kind of say that these networks are black boxes, because you can take the output from any layer in the network, and the activation will always be pretty much always be in a range of -1 to 1 and 0 to 1, and you can visualize it. And I think one of the things you kind of see here is that it does kind of give you some sense of how the network is actually encoding the information. So I'll just look at a single example. Hopefully the connection works to the service I'm going to call. So you can see here we have deposition transcript analysis, and you can see how the convolutions have sort of given different areas of the convolution higher weightings based on the text that's being fed into it. So that's kind of interesting in itself. It kind of gets more interesting if we maybe look at an example that kind of shows maybe something that's a bit more kind of technically legal. So what I might try and compare is I'm going to compare someone who's processing discovery for claim. So usually legal cases, they have a really kind of set of procedures that people go through. And one of the stages is discovery. You probably see it on TV shows as depositions, where they're gathering all the evidence, they're talking about what evidence can be input into the case, or can be taken into account in the case, doing initial interviews and all that sort of stuff. So in this case, it's someone who's doing that work, which is kind of very low level, kind of manual administrative type work. And I'm going to give another example of someone who's drafting an answer to a claim, which is a very different type of work. It's a draft answer in relation to a claim. So usually in litigation, and I've only kind of really picked up this legal stuff since I've been working for this company, but usually in litigation, people have claims and counterclaims. It's a very kind of specific kind of legal type of action, and this is a draft answer, so a counterclaim basically to someone else's claim. And if we look at the I suppose the heat maps generated by the convolutions, we can see that they're quite different in terms of what the network is actually recognizing in terms of the salient features for classifying the type of legal work that's being carried out. Interestingly as well, actually, I just got Pearson's R-square on the 2 arrays output by the convolution, and you can see that the R-square value, or sorry, the R value is actually really really low. So from the point of view of the model, and this is all feeding into a classification model, even though from a layperson's point of view, you'd say this all relates to a claim. From a legal technical point of view, they're actually very different types of work, and the model is actually activating very differently for these kind of fairly nuanced differences in legal descriptions. Okay, I've kind of one other kind of example. Everything we've been talking about so far, we've been talking about, or I've been talking about, I suppose, a model which is trying to classify the legal content of the work that was done. We have other models which do other things, but sometimes it's not very clear what the legal content of the work carried out is. So if I let's say I met Murphy and Co, and I'm going to compare that with call with Michael from Bright Flag. And you can see, I suppose there are kind of two things you can see. One thing that I thought was really interesting is you can see that the convolution or the activations output from the convolution are really, really noisy. So the network isn't quite able to kind of find something that corresponds, I suppose, to a legal task. I looked at it and I kind of thought that entropy would be kind of be a good measure for kind of the amount of redundancy that we have in this in this diagram versus in the other diagrams, and you can kind of see that the entropy is kind of is much higher for these two examples. The entropy, sorry, is in the brackets at the top of the diagram than it was for the previous two cases. So I think that's kind of interesting from 2 points of view. You know, one thing you can kind of see how you can introspect these networks. You know, they're not actually black boxes, and you know, it's always worth visualizing them, and it's always worth actually assessing other metrics as well to try to improve your performance. In this case, I suppose the visual analysis sort of led me to kind of think, well, it makes sense maybe to look at the entropy of the arrays, but it's kind of one of those keys you can potentially use to kind of to train your model. In this case, I think if I was retraining this, what's more important here isn't necessarily the content of the individual sentence. It's the context overall. You know, so I possibly feed this into, you know, some sort of recurrent net that could discover the context in the surrounding lines and the surrounding work that the lawyers are carrying out. That's it.
Have you thought of using this methodology to analyze commit messages of open source projects and try to train your network and find context in these messages?
To analyze what, sorry?
To analyze the commit messages in an open source project, say, which is like
you could, yeah. I suppose probably the technology would work. The question is probably what you want to classify. You know, maybe
let's say try to rate the messages if they are contextful, if they convey information, or are useless commit messages.
Yeah, I think it makes sense. I mean, the key is just like it's a supervised classification task. So I mean, if you're talking about whether something is contextful or not, it probably depends on the context that you're actually doing that in. You know, so I mean, I think maybe the really interesting thing to do there would probably be to see, you know, I don't know, commit messages versus it's likely that a bug relates to that commit at a future point in time. Like I think that would probably work really well. But like it's a supervised classifier, so you need something to enable the network to learn.
You need a training set.
You need a training set, basically. Yeah.
You started out to talk with the old way that things used to work with, like emphasization and tokenization and all that kind of stuff. So presumably there was reasons for moving along from that. How much better, how much superior, faster, less error is the new than the old?
It was a big improvement in accuracy. Like you're talking about kind of a 10-12% increase in accuracy, and it's been really consistent as well. So we haven't moved everything over to a new methodology. We started on a test project, worked really well, and it works really well. I mean, not just from the point of view of performance, but from the point of view of development as well. It's just much quicker development. You spend an awful lot less time. You know, the old 80-20 rule, spending 80% of your time on sort of data preparation and data cleaning and memorization and all that sort of stuff. And you can find that using these techniques, we can do things much more quickly, we can iterate much more quickly, and you know, they're really flexible. You know, just because we started using these methodologies, it doesn't mean that we're not doing things like taking in, say, part-of-speech tags from older models we're using in internal network. You know, we're still using that stuff, but it's just less and less of our day-to-day development work.
I have a question about the training data. How do you, were there like your clients already labeling it themselves, or are they doing that now, or is it like a passive process from history?
It's sort of a mix. I mean, it depends on a client-by-client basis. So there is sort of a categorization schema that people kind of use for kind of legal task definition. The problem is they're lawyers, and they'll usually try to kind of get around the codings, or applying coding doesn't necessarily actually tell you what they're actually doing. So we use some classification data from clients where they provide it, and we also have a team of analysts we use to actually annotate data So we kind of have our own data model, also kind of multiple levels for different types of leader work, and then we have a kind of a gold standard training set basically that we have a team of analysts who annotate that.
I have another question. I assume you do a lot of entity recognition as well. Could you explain in 30 seconds how you approach that kind of topic?
Yeah, I mean, entity recognition it's a big part of our work. I mean, we've kind of found that using, well, it's kind of an ongoing project that we have at the moment, so there are kind of a couple of different parts that, from our point of view, we get pretty good results using recurrent nets for entity recognition tasks. What we're kind of trying to figure out a quick or an efficient way to do is, once you've taken those entities from the text, figuring out who they are in the context, how they relate to the case, is a little bit trickier, particularly to do it in a way that doesn't involve any manual input. So the entity recognition itself, we've kind of found that even out of the box tools, as someone mentioned Spacey earlier on, works reasonably well for entity recognition. If you train it, it works very well. Yeah, we found that kind of, because of the nature of what we do, we're not just interested in identifying entities. What's kind of more important is figuring out who they are in a particular context. Any questions?
Hi, how do you sort of keep up with innovations in this field? Would you be reading like papers as they come out, or does it just naturally sort of trickle down via word of mouth and online buzz?
Yeah, I think events like this are really good. Like the Dublin data meetups, there's a load of meetups that happen locally that I personally anyway kind of find really good to kind of keep up with what's happening. And obviously reading papers and kind of seeing what's happening online as well. But you can't beat community. You can't beat people you work with or people you meet in a meetup. Because it's just you get a lot of insights about what actually works as opposed to maybe what might be a bit of hype. But